All right. Let's see. Zoom meeting was a bust. So we're gonna try this just here. I don't know. My computer keeps freezing. No idea what's wrong with it, but whatever. Okay. So let's just deal with it. So this morning, it won't be in the. I mean, I don't have it. So we had gotten through a little bit of this. So I'll just, we'll redo this. It's cool. But what we're doing here is we're comparing really linear and exponential growth. Okay, and if you're wondering, this is actually, if you have the paper packet, that's where I'm getting these papers from. This is page 93 through 96 on week 5's paper packet. But we've got linear and exponential growth. Yeah, there's a little quadratic, whatever. It's okay. How do they compare? All right, so first let's start with linear and exponential. Okay, two functions. They were small, so I wrote them out again. We had 3x, right? So 3 times x, linear equation, okay? And then we have 3 to the x power, okay? Big difference between those two things. This one's 3 to the x power. So let's take a look at their tables. All right, in their tables, and this is also kind of hard to see, but it goes from -6 to -3, which is +3, right? -3 to 0, that's +3. 0 to 3, +3. 3 to 6, +3. You get the idea, okay? This is an add pattern, all right? So that's why we said add for linear patterns, all right? For exponentials, you'll notice they go from like easier ones, say 1 to 3, you can multiply by 3. And then 3 to 9, multiply by 3. 9 to 27, that's also multiplied by 3. So exponentials are multiply patterns. All right, so that's kind of that's the idea between those two. Is linear is going to be an add pattern, and then exponential is going to be a multiply pattern. So we can look for those hints in there in the tables. Now for graphs. Okay, graphs, those ones aren't too bad to look at here. We can zoom in on this guy. The same two equations, right? Here's our linear guy, our y equals 3 to the x. Notice it's a straight line, okay? And then exponentials, my multiply pattern. This is the red one here. 3 to the x power, right? Starts off flat and then goes up really fast. It's a curve, all right? And it's not a U shape like a quadratic, but it's going to be an exponential pattern where it kind of shoots up really fast. That's what we got going on with this one. So that's what we can tell from the graphs, which one's which, all right? So that's kind of the idea. Let's see. We started on the first kind of like practice problem down here. We started on it. So let's take a look at what we've done so far. All right. So far, we had recognized that this pattern in this table had to be +4. All right. We could have started off looking at this and saying, okay, 4 times 2 is 8. But then 8 times 2 is 16, not 12. So we couldn't do a multiply pattern for this. We have to do an add pattern. So that's what we did. We're adding. Okay, adding 4 every time. So the first one, what's the missing number in the table? Well, it was add 4 every time, so I just added 4 to 12, and I got 16. I even plotted that point on here, too. This guy would be, what, 416? Okay, looks like the y values are going by 2s. Now, here, some of the graph is shown. The graph shows which? A linear growth, quadratic growth, exponential growth. Well, that is an awful lot like a line to me, so that's got to be linear growth, right? It's a line. Okay, so that's linear growth. All right. If the pattern continues, what value of y would be associated with x equals 6? So it's almost like we're adding on to our table here, right? When we add 1 in the x direction, right? We add 1 in the x direction. We've been adding 4 in the y, so we would add 4 to the y value right here, and we get 24. Okay, so that'd be 24. All right, so that's how we can deal with those ones, all right? You just got to make sure that you're following the pattern. And then we just continued it. It's like we continued. This is stuff we did when we first started. Don't tell anybody. Well, actually, I mean, it doesn't matter if you tell anybody. This is literally, I'm following the scope and sequence. This happens every year. All right, complete the table for the function y equals 2 to the x. Okay, so here I'll zoom in here. Here's our questions. Complete the table for the function y equals 2 to the x. So here's our table over here. Okay? There's our table over here. Y equals 2 to the x power. Remember, this is a multiply pattern because we're going 2 to the x power. It's an exponential. It's an expo. So that makes it a multiply pattern. So to multiply 1 to 2, so that means you multiply by 2. 2 times 2 makes 4, times 2 makes 8, times 2 makes 16. There's our first one we get to fill in. And then times 2 again, we get 32. All right? So that's how we can fill in the table. We know it's an exponential just from the equation. We can recognize that, right? We've done a lot of work with these exponentials. And then we just got to recognize, oh, well, that factor, that thing we're multiplying by is going to be that base. So it's times 2 every time. And actually, we could see the table. We could look at the pattern already. So on to 5. Okay. Which of the best describes how the y values are increasing from one interval to the next? When they say interval, what they mean, like, they're saying like 1x value to the next, to the next, to the next, to the next, to the next. What is the pattern? What are we doing every time? We're multiplying by 2. So that's right here, multiplying by 2. Okay, exponentials are always a multiply pattern. All right, we're multiplying by 2. All right, and again, our hint is that there's our common factor. There's our growth factor, as it's called sometimes. Growth factor with exponentials. Okay, it's that base. It's whatever that number is. That number was 2, so we're multiplying by 2 every time. All right, so here we go. Let's look at this. I haven't even looked at this part. I don't even know what this is. Okay, choose between linear and exponential growth. Which job option is better? Option 1. $30,000 this year and a $500 raise each year. Okay, so this is a constant. We're getting a $500 raise each year, so it's like we're adding 500 each year. Okay, being that we're adding linear growth. Okay, it's a constant growth. Okay, it's just gonna be the same thing every year. We're constantly giving you the same raise of $500 every year. Okay, so that's why it's linear. Okay, option 2 says $30,000 this year and then 3% raise each year. So it's a percent increase. All right, it's going to depend on how much you're being paid the last time. Okay, like if you're making $30,000 a year and you get a 3% raise, that means the first time you're going to get $300. All right, well, no, $900. 3%. 3%. Oh, whatever. I'll do it later. All right. It's not going to be the same every year because it's a percentage of what it was. All right. So it changes every time. So percent increases are exponential. Those are expo. All right. Anytime it's talking about a percent increase, it's an exponential problem because it's talking about a multiply pattern. Really, you're multiplying by that percentage. All right. So this is a multiply pattern. All right. Now, in the long run, exponential growth always exceeds linear growth. All right. So as long as something's growing exponentially, eventually it'll catch up. So like in the beginning, maybe that that percent increase, that exponential pattern doesn't give you as much money in the beginning. But over time, that'll start to really build. Moral of the story? Always, moral of the story, exponential growth will beat linear growth every time. All right? So next, which of the following situations represent linear growth? So we need to be able to look at a situation and see which one's going to be linear, which one's going to be exponential. So again, linear, we're looking for adding. We want constant growth. So it's the same thing every single time. Every single time. Every growth is going to be adding the same thing. All right. Martin's savings account increases because he deposits $25 each week. All right. $25 each week is constant. Okay. It's going to be the same thing every week. All right. That's linear. Absolutely. You're adding the same thing every week. Linear. Okay. Callie's pay increases by 3% per year. We just talked about that. Percent increases are exponential. So nope, not B. All right. Each week, an athlete getting into shape loses 2 pounds. Okay. You may think like, oh, it's constant. They're losing 2 things every time, 2 pounds every time. But here's the issue with that. Losing 2 pounds, this is not growth. Yes, it's constant, but it's not growth. We're looking for growth, meaning things getting bigger. If somebody was like, I'm adding 2 pounds every week, I don't know who would want to like be proud of that unless they're putting on muscle or something. Then then that would work. But this one, we're losing weight, all right? We're talking about linear growth. We want things getting bigger, okay? Maylin earns $9 an hour at her job. Well, it's $9 every hour. That's constant. Never changes. Absolutely, that is linear, right? That's constant. Okay, $9 every hour. All right. Next, we're looking for exponential growth. All right. So this time we're not looking for the constant growth. We want those percent increases. We want multiply patterns. All right. The number of butterflies in an area increases. Again, we're looking for growth by 10% per year. Absolutely. There's that percent, right? This is going to change, right? This is a multiply pattern. Absolutely. There's our percent. That's what we're looking for, our percent. Okay. So A, again, that's going to be an answer. Let's see. The population of a city increases by 500 people each year. That's constant, right? We don't want constant. We don't want constant. Christy bought a collector's coin worth $2.15, and its value increases at a rate of 3% per year. Again, we got that percent. Okay, you got a percent increase. Boom, exponential growth. All right. The number of people who have heard a rumor increases because every person tells 2 other people. Okay. So think about it like this. This one actually takes a little bit of thought, all right? If you start off with one person knowing and then they tell 2 people, right? That person's going to tell 2 people, right? That'll be 3 people that now know, right? Okay? So we're just trying to make the pattern here, okay? If then we say those 2 people that now know somebody, you know, whatever, those 2 new people or whatever get, you know, they tell somebody else, well, we've got the original 1 that's already there. We got that 3, but then there's 2 extra people that are adding to it. So really now we're adding 4, so it'd be 7. Okay. This is actually, this is going to be an interesting pattern. It's not going to be anything, though. So, yeah, this is neither. It could have been exponential, but it had the potential to be exponential, but not really. I don't know. I would say no on that one. I might be wrong. I think I printed off the answers, actually. What does that say? 7? Ooh, they do count D. Oh well. All right. I don't know. It's close. But it's like a multiply pattern. It's like multiplying by 2. It's a bad example, honestly. Like, because going from one to the next doesn't really help. But whatever, they're counting that one. Okay. Number 8. What type of growth pattern is represented in the table below? Well, we just got to look. It goes from 0 to 2. So that's plus 2, plus 2, plus 2. Okay, so that's a constant rate for the x's. Let's see what that happens to the y's. Plus 5, plus 5, plus 5, plus 5. So that's an adding pattern all the way. Adding patterns mean it's linear. So this is linear growth. Okay, we're adding the same thing every time, so it's constant. All right, so it's constant. All right, compare that to number 9. 1 to 6 would be plus 5, but if I said plus 5 to 6, I would need 11. That's not the case. All right, so here, 1 times 6, 6 times 6, right? So this is a multiply pattern. This is a multiply pattern, which means this is exponential growth. Okay. All right. Let's see. Actually, the rest of this is for this next week, so that's good. Okay, so that's what we got so far. Hopefully I can edit these things together because there's like 3 or 4 segments that got put together. Again, this is comparing changes in data, linear, exponential growth. Yay!